And for our third speaker this morning, so Rita Fioresi will speak about super quantization.
All right. So first of all, I'd like to thank the organizers for the great meeting, and I'm enjoying immensely both the meeting and the city. So thank you very much. Let's keep working on supergeometry. It's great. So I gave the title of super quantization, though to be honest, I will speak about super representations in more general terms, but okay, so I want to get to super quantization. And these are the papers on which this, I mean, is published, the results that I will explain in a moment. So this is the plan of my talk. I will start talking a little bit about linear supergeometry just to get the notation, and then some very brief account of functor of points, supermanifold, super schemes. Then I will talk about the supergroups and super Harish-Chandra representations. It is nothing but the interpretation of pairs as supergroups as pairs. And then the last 2 points are the most interesting one, the new things, which are the unitary representation of supergroups from both infinitesimal and global point of view. And then the super quantization and super moment map. This is what I will tell you, this is something that results that you are obtaining these days. So it's not complete, but I will express something about this. Okay, so first of all, I know that everybody knows, but just to fix the notation. So we have super vector spaces. I work mainly in complex and, sorry, what is it? A real and complex field. I will try to keep the notation light, but I am not interested in any other field, though it is possible to do things over other fields. Then I note with P the parity. All the superalgebras I'm looking at will be commutative unless I say something different. I know people say super commutative, I say commutative, but okay. And then I look at supermodules, which of course I take A as a commutative superalgebra, and then I look at the free A modules, not always free, and even Latin letter, odd Greek letters. I try to stick to this notation. So this is just to establish what we're talking about. And then I speak about the functor of points. I try to keep this functorial treatment minimal because we heard yesterday, right, talking about these super points. This is somehow the philosophy that knows this very, very well, right? So it's, can I remove my mask when I talk? It's okay. Okay, that knows this very well. So functor of points, what is it? You are looking at, for example, when you have a vector superspace, you are looking at elements as n-nupolls, m plus n-nupolls. And this is identified with all the morphism from this superalgebra, which is a polynomial superalgebra, to A, which is a generic, right? Why? Because as you can see down here, you see you can totally identify a morphism when you specify the generators, and so you obtain this correspondence. So this is a very, very basic fact of supergeometry, and I'm using it extensively. So functor of points as the A points of some object. Then what is a supermanifold? For me, a supermanifold is an object which is locally. So first of all, you need a topological space, and then you need the algebra of functions, which is locally split in the sense that locally it is a tensor product between the C-infinity functions and an exterior algebra on the odd variables. I put C-infinity, I could put anything there, could be an analytic function, whatever functions you like. And then you can also define the super schemes. These are obtained by looking at something which is the spectrum. I don't want to get into this because it will take us very far, but it is possible to give a generalization of super schemes. And then you can interpret the functor of points. So functor of points are the morphism in the sense of supermanifolds or superschemes. Now here, when we talk about supermanifold, C infinity, morphism are easier. Why? Because they're recovered globally. For superscheme, that's not anymore true. I don't want to get into this very long story. It's just to establish the notation. So when I talk about morphism, we know what these things are. And if we don't, that's okay, because this is not a course in supergeometry. So, and just to get a feeling, because I'll be speaking a lot about representations, you can look at the general linear supergroup. One way to look at it is through a points. That's not my favorite point of view, but I just want to say that it's possible. So in this case, you look at your general linear group as matrices with entries in some commutative superalgebra, okay? And again, I repeat this just for establish also the notation, is that if you give me these generators, see this polynomial algebra, so to speak, because this has infinity functions, you can retrieve any a point just by looking at morphism. See, a morphism gives you one of these matrices. The set of all morphisms gives you all these matrices. And the fact that you are in GL is recovered by the statement that you want the diagonal blocks to be invertible. Okay, this is, I mean, we know this very well. It's just to get to the point. Okay, so this is an example of this very fruitful point of view. Now, when we talk about actions, it's very good to look at the function of points. Unfortunately, when you look at infinite dimensional actions, I will be looking to those also, function of points is less good. We see what to do, okay? So it's pretty clear, right? When we have a point, it's great. I mean, Ekaterina was speaking to us about Grassmannian, that's perfect, right? You have action of GL, you have the Grassmannian, look at the orbit, is wonderful, that works great. But when we look at the infinite dimension, so you want to put here an infinite dimensional space right here instead of KMN, that you encounter some difficulties. And this is what I want to go into. Okay, so this is everything clear so far. I mean, this is like a very quick crash course on supergeometry. Now we go to a more technical point of view. So in the previous talk, thank you for introducing the pair. So I like to call them, I like to call them super Harish-Chandra pairs. And I will try to explain why I use this terminology. Those people that know Harish-Chandra representations well realize why I'm using this term. But anyway, it was not invented by me, of course. I think the first occurrence of this, and I hope you guys forgive me if I'm not giving the right attribution, is due to Kotzul. I think he is the one, but I'm not. Huh?
Perhaps Ninehurst.
Ninehurst. Okay, I'm sorry. It's impossible to keep track who did the first. So you can take a supergroup G and associate what is called this super Harish-Chandra pair, which consists of a Lie group G0, which is the underlying topological space, and then a G Lie superalgebra, which has the even part. The even part of the Lie algebra is just the Lie algebra of the Lie group. But then that's not enough. You want G0 to act in a nice way so that on G0, it is the adjoint action, some compatibility, right? So take a supergroup, you associate a super Harish-Chandra pair, and there is actually an equivalence of categories, meaning that give me a supergroup, super Harish-Chandra pair, give me super Harish-Chandra pair, there is a one-to-one correspondence, which is also behaving nicely with respect to the morphisms. And I don't want to go more into this. This was used in the past. I wrote something about it, but many people wrote it. So it is really difficult to give attributions here. Many people knew this equivalence of categories. So the example For example, if I take a GL, then you have the G0 is just the diagonal block matrices, and the GL is, well, is just the vector space of super matrices with the parity. So this is, and the bracket, I mean, is almost insulting writing super bracket because you all know what it is, but just to give you a feeling, yes, this is what everyone knows. So it is not something particular, okay? But now we have two ways of looking at supergroups. And if I tell you GL, actually I'm telling you a lot, because the supergroups I'm personally interested in are the so-called, you know, the supergroups corresponding to contragradient superalgebras, right? So actually they're all subgroups of GL. So this really contains all the things I'm interested in. I thought it doesn't contain Q. Well, it contains Q, but I'm not doing a Q. I'm sorry. Okay, so since we said that there is this equivalence of categories, I can look at the representations of a supergroup in a vector space equivalent as an action via the functor of points, or as a natural transformation, or a super Harish-Chandra representation. That's the point of view that I will take in this talk. So what is a super Harish-Chandra representation? So you take a representation of G0, right? This the underlying Lie group in the space where you take it on the even part of GL morphism, and then you want a representation of the Lie superalgebra. So you want a pair with some very natural condition that when you see you have the adjoint action of your group, it will intertwine this adjoint action, very recent. And in fact, as we're going to see presently, this is the condition that Harish-Chandra himself put down when giving the notion of Harish-Chandra representation for groups, for Lie groups. This is supergroup, right? Harish-Chandra was doing. So what is the equivalent that Harish-Chandra was thinking? Okay, yes. What capital X? X is an element in the G superalgebra. Excuse me?
Small g.
Right. In the Lie algebra G, right? So what was Harish-Chandra? What is an Harish-Chandra pair? An Harish-Chandra pair, if you give me a Lie algebra, so if you give me a real Lie algebra, there is a unique maximal compact. You can write the Cartan decomposition, and then the Harish-Chandra pair is that you take a complexification of G, so you have a complex Lie algebra, and the compact maximal that determines the real form. That what was Harish-Chandra thinking. I will have a slide on this, but now it is the time, because you see there is a pair for us, the Lie group and the supergroup. For Harish-Chandra, it is the so the pair for us is the Lie group. For him, it is the G0 is the compact, maximal compact, and G is the algebra of the Lie group. So this is the analogy. If you don't see the analogy, that's okay. It's just to motivate the name, it's not substantial. So I wanted to give a little feeling on how these representations work. This is a very, very modest thing. I mean, this is not, of course, I don't want to say I did it because, I mean, this is very well known, but just to get a feeling. So we look at the OSP. So if we look at OSP 1, 2, and yesterday we were looking at it when looking at the Siegel superspace. I will also look at the Siegel superspace. So we saw this already yesterday. So the OSP, real or complex, it doesn't matter at this stage. It is the even part is an SL2K, and then there is the orthosymplectic superalgebra that has this form right here. So it is OSP, which is generated, well, this is the 3 SL2 generators, and then you have these odd generators with these relations. I mean, there are other relations that I did not write on. Yesterday, we saw this very, very clearly. And then you can prove that if you look at the representation of OSP 1, 2, in terms, of course, Katz did all the algebras. I'm just elucidating this special one. So if you have a look at the highest weight representation of this little OSP group, so it is it consists of two SL2 representations that are highest weight, one of V0 and one of V1, and then you have the odd element X that moves you down, and the element Y, which I did not write, that moves you the other direction. Okay, so it moves around. This is well known, and yeah, so you can really express it very clearly. Now, what I'm after? I'm after a unitary representation. So I want to put a Hermitian product on this representation and see what are the conditions that you put on the weight. Okay, that is the goal. All right, so let's see how we go about it. One defines what is a super Hermitian product, and to be honest, it is something that anyone can do, because when you switch, you put a bar. This is, what can I say? It is very, very, very obvious. And you can define what the adjoint is, and of course the adjoint will come as sign. And then there is a very horrible thing, very ugly, I think, that since there is a minus sign coming when you have odd elements, you can pretend that you forget about even and odd if you put an I, right? I mean, this is a very stupid thing, because since you put a bar, when there is a bar, I comes with minus I. So this is essentially what happens is that you can decide if you want to work with ordinary Hermitian product, okay, or you want to work with super Hermitian product. It's up to you. Authors, of course, choose different things, but any Hermitian product, you want these two to be orthogonal. This is a requirement, okay? So let's just see what conditions we have on, say, highest weight representation to obtain, yes?
You require a positivity.
Excuse me?
So does your notion include positivity?
Yes.
So I think the last, well, when you say that you get ordinary Hermitian product,
yes, yes,
means that you impose some positivity.
Yes, but it is very irritating because so there is a choice of a sign.
Yes,
right.
I know.
Yes.
Yeah.
So is immaterial, this sign, but you want that the sign is the same in the two blocks, right?
Yeah, yes. So, but
yes, I want to impose.
But
that.
you don't have any non-trivial signature in each of the pair.
No, I don't want. You know, that is.
Yeah.
But you know that the two signs have their own lives, so to speak.
And you don't consider odd Hermitian products.
No.
So you only
yes.
even.
Yes, yes. I follow some authors do this. It's not me. Aldridge, for example. So it is. Okay, so okay, then we give the definition of unitary representation is exactly what you expect. You want the representation to have the adjoint equal to minus. I mean, this is something that we learn really in a very basic algebra course. And actually here I put down the proposition in which Carmelli, Cassinelli, Tolgo, and Varadarajan write this. I mean, this is really again the curse of the minus side. That is not very what can I say, substantial. What we are looking at is not a finite dimensional representation, but infinite dimensional representation. That is the point. So this will be operators in some Hilbert space. So there will be all the problems connected with this, okay? And that is the whole thing, not a finite dimension. Okay, so here is the definition of representation from a Harish-Chandra point of view. So we take a supergroup, which is real, which means that both G0 and G are real. What is a unitary representation is a morphism in the from G to the automorphism of some Hilbert space, which is equipped, you know, with this with this form, Hermitian form, so that you want pi 0 to be an even unitary representation, and you want the differential, whoops, the differential, you want it to land into the analytic vectors. This is a very understandable. And you want H to be the completion of V. So this is really the same definition that you would give for the classical, the ordinary setting, except in the super. And you want to construct these representations, right? For a real supergroup. That is the point. So the goal that we have is build these representations. First of all, we build from we show they exist. But we're not happy with that, so we build them geometrically. We build them geometrically in the space of sections of certain line bundles. And then we're not happy with that anymore, but we want to do the geometric quantization point of view, which is we want to build the so-called model. We want to realize them all at once, and then they will be realized in a certain symmetric space. But I will keep going and it will be clear. But so we're really following the ordinary theory and see where it will lead us, okay? And I know here there are experts in everything, so please stop me anytime, okay? So we start with our assumption. First of all, we are very, very general because for the existence, it is simple. Well, no, it's not simple, but I'm saying for the existence, you don't need to put other hypotheses. So we take just a real Lie superalgebra. For example, we take a contragradient. We just ask G0 to be reductive. Then we take a representation. We look at the supergroup that has G as its Lie superalgebra. And we ask that V is finally generated as G module. So, for example, highest weight, yes, it is finally generated by the highest weight. And so this is. And then we prove this result. So the result is that there is a unique, so if you get a simply connected Lie group defined by the G0, there is unique unitary representation on the completion of V, okay? So essentially, if you give me a representation of the Lie algebra, sorry, the Lie superalgebra G, you can integrate the representation to the simply connected G0, okay? And you get a unitary, no, sorry, not unitary, yeah, unitary, unique unitary representation of the supergroup, okay? So this, so essentially tells you any unitary representation is integrable to a unitary supergroup representation. Okay, so this is integrability of representation. This was done by Aldridge before us. He was proving this. We prove it with a different setting of, what can I say, we are more general. And also we use different methods. He's using more analytic methods. We're using more algebraic method, but okay. So this is this is an existence result. I know it doesn't make me happy because one wants to know what these representations are, okay? So now we're looking at some more specific representations, the Harish-Chandra ones. So I look at unitary, now I look at Harish-Chandra, and eventually I will look at Harish-Chandra unitary representation. So we take a complex vector space, super, of course, and I think about infinite dimensional ones. Now I look at GC, a complex contragradient superalgebra. So I'm putting myself in a very specific situation. And then I look at the Cartan decomposition of this algebra. And so, for example, I put here an example. Now it's really this, the SU is what you were saying, right? So this is an example where you have mixed signature, right? And and then you want to look at the representations of these objects. Now, here is the definition of what is an Harish-Chandra representation of module. So look at this. It's, I think, very nice because you see you have a representation of the real compact and that representation of the Lie superalgebra, and you want this adjoint condition. If you remember, that's exactly the condition we had for the super Harish-Chandra pairs, right? So it is the Harish-Chandra representation inspired the definition of a super Harish-Chandra pair, because that's it. And then you have these extra two conditions that they're not in the Harish-Chandra, super Harish-Chandra pairs. You want this representation to decompose into isotypical components for the complex, and each isotypical components must be finite dimensional. So, well, of course, since you're looking at this decomposition with respect to compact, then each irreducible will be finite dimensional. But you are asking that the sum of all irreducible of the same character to be finite dimensional. I want to make a remark here because you are taking K to be even, okay? So the compact is even. And you may wonder what happens if the compact is also bigger than just the even, right? This is an interesting question that we don't have an answer right now. I'm thinking with other people, with my co-author Gavarini, we're thinking about this generalization. But I just want to warn you that if you're looking at Cartan decomposition for Lie superalgebras, remember that it's a bit different in for the type 1 and type 2 superalgebras. The type 2 do not allow a compact form, okay? So it's taking K even, somehow it is a justification, because for the type 2, you cannot make it more than that. Type 1 is more resilient, because type 1, you can really take the maximal, for example, SUPQ is a compact form of SL, SLN, SLPQ, right? OSP doesn't have a compact form. Exactly, that's the point. So taking K even, it's I mean, it's not the best you can do, but it has a justification, so to speak. Okay, so we're looking at, yes. Oh no, okay. So you were looking at this representation. So now I come to your favorite slide here. So we're looking at the Harish-Chandra morphism. Here, you can build a morphism from the center of the superalgebra to the polynomial invariant by the Weil group action. There is a little bit of a translation. I don't want to get into this, but it is very important, this theorem due to Katz. It is the one you were referring before, right? Saying that the Harish-Chandra homomorphism identifies the center of the universal envelope superalgebra, which is with a subalgebra, okay? So this is a new super phenomenon because the Harish-Chandra homomorphism identifies the center with the invariant polynomials, but for super, no. You go inside, this is a subalgebra of that. It's not the all Weil invariant. Yes, I know, Ted. I knew it before.
No, I just wanted to say I'm not quite sure that in full generality, but there is Berezin's work, which was before Katz.
I am sorry.
So I guess the example, what you're saying, that is just for general linear supergroup. Well, for invariance, so when you have Weil group, simply means your functions of eigenvalues, which are symmetric separately in the even sector and odd sector, but plus extra condition, which is given by some differential equation. And this is probably, but this was in Berezin's work.
I am so sorry. I knew it already that I could not give the right attributions.
No, but Berezin's work is very not very well known, unfortunately, because it was in a series of preprints and which was not properly published. So the preprints are known. So they in the English version of his book, which is published after his death, so these preprints are collected together as a second part of the book. Okay. But again, the book is not so well known.
I promise I will look.
Yes.
But this theorem by Katz actually it was not even easy to find this, right? Because he states this into a paper that is about something else, which I forget, and he states it at the very end.
Not about classification, not his paper on classification.
No, it's a much obscurer paper that is like, I don't know, 4 pages long, talking about something totally different, and suddenly in the end there is this.
Right. Okay. Okay.
It is a very, I don't know, it looks like one of what is called scavenger's hunt in English, right? It looks like that, right? Okay, so, but we have this Harish-Chandra homomorphism, and then we produced with Carmeli and Varadarajan the following result, that if you give me an irreducible highest weight representation of highest weight lambda, then it is unitary if and only if you have this condition on beta. Beta is the Harish-Chandra, beta is the Harish-Chandra homomorphism. And for all A in the super enveloping algebra, and star is an anti-automorphism extended the adjoint, right? So this is actually, I must say that in the proof of this, we didn't do anything special. We are copying Harish-Chandra proof. It's really the same. Everything goes through. And so it's what Harish-Chandra does. He uses this extension to build a scalar product and then proves that it is well defined. I mean, it satisfies all the nice properties. And so it is, so we copy Harish-Chandra. But in order to have irreducibility, there is a necessary condition that is the Harish-Chandra cone condition. You want your weight to be positive for compact roots, so roots spaces that sit into the compact subalgebra, and you want negative for the non-compact one. Now, this is a condition that is really necessary. If you don't have it, it doesn't work. And just to give a feeling, what is the Harish-Chandra cone? It is really a cone. So if you are in SL2-1, you have one even simple root, one odd simple root, and then the sum of the two is odd. And then if you look at the conditions, you compute it has to have a positive scalar product with the even, negative with the other. So it is really that. And you have this very geometric cone. Okay, so we also had an example because we felt like that the theory is not happy if you don't have an example. So let's take a universal Verma module of highest weight. You can take any complex number. So this is the representation I was showing a moment ago. Then we prove that this highest weight is a unitary if and only if T is real and negative. And in that case is irreducible. Now, then our theorem proves that you get the representation of the supergroup on the completion of this Verma module. And yeah, so you just obtain very simply. It's just an exercise, but we figured that it was nice to have really something that you can touch. I mean, you can tell what are these modules, what is that you do. Now let us do now what I was saying at the beginning. So we prove that you can integrate a representation, that you can construct unitary, but the question is, where are geometrically? I want to give a geometric realization. This is really the work of Harish-Chandra. Harish-Chandra was constructing the so-called Harish-Chandra representations on the line bundles on symmetric spaces. That's what we want to do. So we're really following this program. So we get a real supergroup, for example, SU, but any supergroup. We take a maximally compact torus, here imaginary diagonal, then a maximal non-compact torus, and then a contradigradient superalgebra. We ask that the rank of the maximal compact is the same as the rank of H. So what we're doing, we are asking that a cartan of K is the same as cartan of the whole group, okay, the whole algebra. That is necessary for the theory. This leaves out some, but okay. We have the super Cartan decomposition. So here I write the K for the example of SURS. So this is, if you know Cartan decomposition, it is really what you expect. And then what we want to do is to define admissible systems. Now, this is a little technical. I wanted to put this slide. Usually in my talks, I don't put such technical slides, but here I figure I am among people like me that love these things, so I will put it. Now, why is it so important? This is a discovery of Harish-Chandra. So if you take a Cartan decomposition, K plus P, and you look at the positive non-compact roots, you see these positive non-compact roots must have the condition that P plus sits in K. Yeah, that's the Cartan decomposition. But here is fantastic because it's not true. It sits in P plus. So what happens because of this admissibility condition, actually for non-super, when we are in the ordinary case, the sum is 0. So you don't, the sum of two positive roots in P is 0. What happens is that P plus, this becomes a subalgebra, and this is the supergroup associated. So in the Cartan decomposition, K is a subalgebra, but P is not a subalgebra. But in the miracle of Harish-Chandra admissible system, P splits in two pieces, the positive and the negative, and each of them is a subalgebra. And it is true also for super. And you can clearly see this because if you take the alpha and beta, so if you take alpha as compact and beta as non-compact, the sum is, so if you take the sum of two non-compact roots, this is not a root, so it is 0. So it is a miracle. And what happens with this miracle is that you have this decomposition, the Harish-Chandra decomposition, that allows you to put a complex invariant complex structure on your symmetric space. That is for example, in the ordinary case, GR is SL2R, the maximal compact is SO2. This is a baby case, right? And we know very well that this is the upper half plane that has a natural complex structure. And you get it through this, because this is the Harish-Chandra decomposition. So this guy here, GR Kp plus, sits into the Harish-Chandra big cell of the. And really, if you play this, you can repeat this absolutely the same for super. And in fact, here I wanted to put the example. I put it because I saw yesterday we were talking about the up half plane, and I figured, come on, you can do the super Lagrangian, is the same price. You don't have to do much. And you can, yeah, that's the Siegel super space. And you can prove that it is realized as the real OSP modulo this KR. And it has natural complex structure coming from the complex Lagrangian that we've been constructing. Now, this is the object where we want to construct line bundles on, okay? So we will construct a holomorphic line bundle on this symmetric space. Actually, yeah, we look at a bigger object, but this sits into it. And then on the holomorphic section, we build the unitary representation. That is the, I put this just to have fun, because I figured that it's so nice to have, the Siegel is so important. Okay, so I'm giving you just the result. I will really spare the awful technical details. You build a super line bundle on G mod B that apparently is larger, but it contains the symmetric space. So this is the set of all the, yeah, I should, the holomorphic, H seems like Hilbert space. I wanted to say holomorphic, that H is holomorphic, which transform according to a certain character that we pick. And then on this particular open set that I wrote before, This contains an analytic continuation of the constant polynomial. This guy here, this psi guy, is called the Harish-Chandra element. And then on the closure in the Fréchet, you get a GR representation. Okay, so this theorem that we have tells me that if you look at the action of the Lie algebra, so you take the differential, then you get the highest weighted module for G, which is irreducible for some lambdas. We say that, but I don't want to get into this. And if we take the completion in the Fréchet topology, you get an irreducible Harish-Chandra module for GR. But no unitary. So that's the work we did in 2019. That was the last work of Varadarajan. Then we go for the unitarity. Unitarity is much tougher because if you ever try to multiply odd sections, you know what I mean, right? What is the unitary? If you have a section, you try Hermitian. What is that? You get an odd in your way, right? So this is the thing. So what are the unitary highest weight Harish-Chandra representations among those constructed above? So this is the question that we asked. So unfortunately, Varadarajan was not there to help me. So I turned from some help from someone else. So this is work with Chua Meng Kiat. He was also interested. He is an expert in quantization, geometric quantization. So we took this angle, and I must say it's very nice. So the first thing you can prove, this is not hard at all. You can prove the Iwasawa decomposition. So you take a complexly superalgebra, you take a G real form, A is the real torus, and N minus is, you know, the nilpotent, that is an nilpotent subalgebra with respect to a system. You get this isomorphism, which tells you that GAN is open in GC, so that you can look at this X. This is a main character. So this is the where the space, see, we were looking at symmetric spaces in here. And the idea of geometric quantization is that let's go back, let's get something that is larger, so to speak, and look at all. So here you get one representation, here you get all representations. That is the idea. So X is a wonderful structure because X is a Kähler manifold. So there is a symplectic structure. There is an action of X. There is an action of G from the left. There is an action of the torus from the right. Both actions are Hamiltonian. So it is really a wonderful and fantastic. So I wanted to give an example, but maybe I skip this example. This example was, yeah, better skip it. I want to say the important things. So the question is, I want to determine all irreducible unitary representation of a real supergroup in the space of holomorphic sections on a super line bundle on that, right? So let me do a crash course in geometric quantization in this particular setting. So we have a G0T invariant Kähler form on this, on this manifold, right? So G0 is the real group, A is the real torus. And what is really fantastic is that this Kähler form is globally expressed by a Kähler potential. This Kähler potential F0 is invariant by the action of G0. So it is really very nice. You can build an Hermitian line bundle on G0 with the omega 0 is Chern class. And of course, since omega 0 you can express as D something, it will be trivial as a C infinity line bundle. You know, that's exact, obviously. You can do this. Then there is a unique G0 times T invariant section. And what Guillemin and Chua prove is that, well, as you know, the Chern class is trivial. So it is trivial as a C infinity, but they prove that it is also holomorphically trivial. So there is this section S0 that is holomorphic. This fact is non-obvious because having a C infinity section, it doesn't tell you there is a holomorphic one. So this is the Guillemin result. And then they also prove that the Hermitian product on fiber is given through this notion, because you have S0, see, S0 is a base at each point, is a basis. So if you tell me what is this Hermitian product, you're telling me the Hermitian structure of this bundle, right? So actually, I give the attribution to Guillemin, but Guillemin is some of the cases, Chua did all the possible cases, because when you take a compact form, it's of course easier than when you take a generic form. Okay. So through this global holomorphic section, so the geometric quantization, we take this, we want a line bundle that has the curvature exactly omega, right? That is the game of geometric quantization. And you realize this correspondence because S0 is a global section. So you get this Hermitian product. And then Guillemin and Chua in 2000 proved that I think it's very nice, this result, that the representation, certain representation is realized in this Hilbert space, because we have Hermitian product, if and only if the highest weight lambda is in the image of the moment map. I think this is very beautiful, because the moment map controls whether or not your representation appears in the H2, in the integrable. See, there is this Hamiltonian action, right? So this is, what Chua and I have been trying to do, we want, of course, we want this for the supersetting, and we have everything, right? Because we have, so let me show you what we have. So we take the Hermitian bundle just, I mean, stupidly, we take a globally split line bundle. And then we have, we prove the existence of a superkähler form. We've not been inventing anything. The superkähler form and superkähler potential are around. Physicists have been playing with it a lot. And then, sorry, there is not a K here. This should be a G. We define the moment map in the supersetting. Remember that here we have that omega is exact. So there is a global holomorphic form that is giving us. So I'm just trying to tell you that the moment map, which is kind of a bad object usually, well, not bad, but not so simple to access. Here it's simpler to access because the exactness. And then we give these super representations exactly as before. And we have the following theorem, though I should not, I wrote 2022 because we are working right now. So we have, we take, I forgot a star. We take lambda in T star to be typical, and in the Harish-Chandra cone. We spoke about the Harish-Chandra cone a moment ago. Typicality is because, to be honest, I don't know how to do without it. I put it because it's easier, typicality. And we have the reducible unitary highest weight with a certain super character occur in this Hilbert space, if and only if lambda is in the image of the super moment map. And these representations are given exactly as those sections that transform according to this character. So essentially we put together Harish-Chandra construction and the ordinary geometric quantization to single out among all the representations that we constructed with Varadarajan and Carmeli, those that have a unitary structure. Okay, so that is the idea of our theorem. To be honest, I should have written conjecture because right now we're having problems on the walls right? Because when you take the weight away from the walls of the Weil chambers, so to speak, things are happy. If we take a lambda on the wall, we're still, so I should say, you know, conjecture. For lambda with the wall, we have the theorem. For lambda on the walls, we don't right now, but we're confident to have it soon. Thank you very much for your attention.